Problem one was to simplify the following expressions. 1 minus cotangent squared over cosecant squared. Now, rules of thumb said to start with algebra and put these over a common denominator, and that works just fine, and I did it that way once. If you don't see that right away, you can always go to the, there's no trig identity to immediately apply. Well, not one that helps maybe. You could use the Pythagorean identity on this one, write it as cosecant squared minus 1. Maybe that'd make it a little easier. So there's identities you can apply and so forth. What I did on the handout, which is the third thing, if you get stuck, you can just change it to cosine and sine. So cotangent squared is cosine squared over sine squared. And cosecant squared is 1 over sine squared. And this reduces to then 1 minus top times bottom, cosine squared sine squared, over middle times middle, 1 times sine squared. The sine squareds cancel, and you just get 1 minus cosine squared or sine squared. So that's what I wanted to say on that one. There's other proofs. If you put this over a common denominator or some, for instance, works real well also, but this was one way, was to write it in terms of sine and cosine. Okay? Want to look okay? Stop me when there's any questions. All right, you knocked a minute ago. I thought maybe I heard it. I looked and didn't see you. All right. So that was 1A, and then 1B is this. If you simplify cosine 2 theta, cosine 5 theta, minus sine 2 theta, cosine 5, sine 5 theta. This kind of thing comes up in science classes actually quite a lot, where you're just supposed to scratch it and say cosine, cosine minus sine, sine. That looks familiar. What does that look like? If I think of this is alpha and this is beta, so it's cosine alpha, cosine beta minus sine alpha, sine beta. I recognize that that's cosine of alpha plus beta by the sum identity, right? That's why I wanted you to recognize here. It looks like a sum identity, cosine, cosine minus sine, sine, where alpha is 2 theta and beta is 5 theta. Some of you left it here and I gave you credit, but I really wanted you to add, write that as cosine 7 theta, right? That's the simplified form. That was the trick there, just to recognize it's a sum identity. Reduce it to cosine 7 theta. Questions on that one? Does that look all right? I'd like to be able to do that. When you're stuck, try writing cosine and sine. Maybe it'll help you. This Pythagorean identity, sine squared plus cosine squared equals 1, often comes up as 1 minus cosine squared. It can be replaced with sine squared, or 1 minus sine squared with cosine squared. So this is I think this is a real useful problem. And these kind of things, like I say, often come up in reducing things in science classes. The second one was to write as a product sine functions, sine and cosine functions, using the sum to product identity that's given here. I didn't expect you to memorize that one, as we said. Where I have cosine 5 pi over 12 plus cosine pi over 12. I also gave it degrees, so you wouldn't have to do radians if you didn't want to. 75 degrees and 15 degrees. Either way you do it, I'll do it in radians just for the first one there. The idea is that cosine plus cosine, alpha plus beta, is twice cosine of their sum over 2 times cosine of their difference over 2. That's the sum to product identity. Cosine plus cosine is 2 cosine cosine. So now alpha is 5 pi over 12. And beta is pi over 12. So these. Then you can figure out what these angles are, right? What's this angle? 5 pi over 12 and pi over 12. Well, that's 6 pi over 12. All over 2 maybe makes 6 pi over 24. All right, so you add the numerators over the common denominator and get 6 pi over 12. Then divide by 2, get 6 pi over 24. Here you subtract 5 pi minus pi is 4 pi all over 12 since they have a common denominator. Divided by 2 is 4 pi over 24 if you like. But then these reduce, right? This is just pi over 4, and this one's pi over 6. So what this really is twice the cosine of the special angle 45 degrees times the cosine of the special angle 30 degrees. Pi over 6. So you recall from the special triangles that, cosine of 45 degrees is square root 2 over 2. Cosine 30 degrees is square root 3 over 2. I said right as a product, I should say and evaluate. Now the 2's cancel here, 2 on the top and 2 on the bottom, so I get square root 2, square root 3, square root 6 divided by this 2 that's left in the denominator. Or you can write it as square root 3 halves if you want. Okay, so there's 2. That one seem all right? Given this identity, cosine alpha plus beta is 2, cosine of the sum over 2, cosine of the difference over 2. We can evaluate this one by a sum to product formula. Okay, 3. Some people tried to do this one by a sum or difference identity, but you can't write this as a sum or difference of special angles because it's not a multiple pi over 12, right? You can do any multiple pi over 12 with sum and difference identities, but this is a multiple pi over 8, so you're stuck with the half angle identity. This one you have to use sine of 1/2, 5 pi over 4, which is a special angle. Sum and difference doesn't work. You can't write it as sum or difference of special angles unless it's a multiple pi over 12. It's half angle identity. If I call this alpha, we know that the sine of 1/2 alpha is plus or minus the square root 1 minus cosine alpha all over 2. But alpha is 5 pi over 4, the whole angle here. Is a special angle, and I can evaluate its cosine on the unit circle. Pi over 4 more makes 5 pi over 4. Drop the perpendicular, and if this is a pi over 4 angle here, then this is square root 2 over 2, and this is also, and so the coordinates are minus square root 2 over 2, minus square root 2 over 2. Which means that the cosine is minus square root 2 over 2 in particular. We got 1 minus a minus square root 2 over 2, all over 2. Some people forgot their minus here, huh? And then as a plus or minus, some people said, oh, quadrant 3, it's negative, right? No. The original angle is 5 pi over 8. 4 pi over 8 is pi over 2, right? This would be 8 pi over 8, because that's pi. It's between 4 pi over 8 and 8 pi over 8, right? It's 5 pi over 8, so somewhere in here. It's in quadrant 2. It's in quadrant 2, the sign is positive. So I want this side to be positive. This radical side means the non-negative number that has this square. So it's positive by itself. I don't want to take the minus, I want to take the plus. Right? So I'll say quadrant 2 on the original angle for sine tells me I want plus there. So now the answer appears to be, and is exactly, 1 plus square root 2 over 2, all over 2. But, oh, compound quotients, right? Point off. So you want to multiply top and bottom by 2. Multiply the top by 2 and get 2 plus square root 2. Multiply the top bottom by 2 and get 4. And then you want to get rid of that square root 4, right? Square root of 4 is 2. So let's write it as square root of 2 plus square root 2 all over 2. So there was the answer I was looking for in that one. Problem 3. do 4 here. Put that off the edge last time a little. Sound up in case you want to talk online. Four has established the identity. Sine squared 2 theta equals 4 sine squared theta cosine squared theta. If you're clever, you can just recognize, wait a minute, that's the square of the double angle identity. If you just wrote that, I give you full credit. But here's an easy way to write it in a little more detail. Sine squared means take the sine and then square it. That's what this notation means, right? Now you write the double angle identity as 2 sine theta cosine theta, and that's it, right? Because 2 squared is 4, sine squared is here, cosine squared is here. There it is. So that's all there was to that one. Some people just wrote square root of this one equals square root of that one. That's true, but that's also like proving x equals 2 by taking the square root of both sides and saying, oh, x equals 2. Well, x could be minus 2 and the square is 4. So technically that wasn't quite a proof, but I didn't complain. When you say they're both the same sign, plus or minus, then you can take the square root of both sides and say it's a proof. But well, I like this way better. Here's this one. I was pleased on this one. Pretty much everybody got it. Sine theta minus 7 plus 7 equals 0. And I said solve for theta in 0 to 2 pi. You subtract 7. If you had 3x plus 7 equals 0, you subtract 7 and divide by 3 and get x equals minus 7/3. You do the same thing here. Subtract 7, divide by 3. And get equivalently sine theta is minus 7/3, right? Oh, wait a minute, that's less than minus 1. There's no solution. That's all there was to that one. How about that? If you want, you could graph it and see that if you don't recognize it. Say, oh, sine is the y coordinate. Here it is. The minus 1 and up to plus 1. I want the y coordinate equal minus 7/3. That's way down here, right? There are no points on the unit circle that have y equal minus 7/3. There's no solution. So if you sketch it, you'll see it. But all you have to do is this. It's less than minus 1. Sine is a number between plus and minus 1. That doesn't work. Okay. Again, simplify by the half angle identity. I give you a hint. Simplify by half angle identity. Square root 1 minus cosine 11 pi over 12 all over 2. How do I make that simpler? I remember the half angle identity that square root 1 minus cosine alpha over 2 plus or minus is equal to with my plus or minus. Well, this identity, if it's plus or minus, if this one is plus or minus this one, it follows that this one is plus or minus 1/2 L. Well, let's write it with the plus or minus on the other side. And say, does it need to be plus or minus? The radical sign means the non-negative number, so this is plus. This angle in here is 11, 1 times 11 pi over 2 times 12 is 24. Well, this is less than 12 pi over 24, which would be pi over 2. It's in quadrant 1. Which makes this positive. This is positive, so I have to use the plus sign here. So a plus and plus come up. So the answer is sine 11 pi over 24 to make it positive on both sides. Okay. Number 7. Let's see. 7 says, use the double angle identity. Find cosine 2x if the cosecant of x is square root 5 over 2 and cosine x is negative. On these where I say find cosine or sine, a trig function of a double or half angle, what you do is write down the double or half angle formula. Cosine 2x is cosine squared x minus sine squared. You write that down, then you figure I need these. How do I get that from what I have left? I'll just over on the side somewhere go figure this out and say, well, taking the reciprocal of this equation, reciprocal to the left is sine x, and the reciprocal to the right is 2 over square root 5. That gives me one of these two that I know. Then what some people did, if you replace this with 1 minus sine squared, then you're done because you've got sine. The alternative is to do this, say cosine x immediately is plus or minus square root 1 minus sine squared. And we're given cosine is negative, so let's use minus. Minus square root 1 minus 2 over square root 5 squared. This minus the square root of 1 minus 4/5, right? Square root 2 and square root of 5. Minus the square root of a fifth, or minus 1 over square root of 5. So what I do is I write the double angle identity, then I compute sine and cosine on the side, now I'll put them in. Minus 1 over square root of 5 squared for cosine squared. 2 over square root of 5 for sine is squared. This gives me 1/5, right? The minus is canceling. Minus 4/5 by squaring is minus 3/5. So nice fraction. How about that? Despite that nasty square root here, it went away. That should be exactly minus 3/5. Any questions on that one? Is it all good? Oh, here's number 8, the last one, hardest one. Save it for the last. Solve for theta between 0 and 2 pi. The equation 2 sine squared theta minus sine theta minus 1 equals 0. My suggestion is write u equals sine x to recognize a quadratic equation. This becomes 2u squared minus u minus 1 equals 0. There we go. And you can solve that either by factoring the quadratic formula. I think I said, let's see, use the quadratic formula. So we use the quadratic formula. U is minus b plus or minus square root b squared minus 4ac all over 2a. That's c. A is 2, b is minus 1, and c is minus 1. So it's minus a minus 1 plus or minus square root minus 1 squared minus 4 times 2 minus 1. Some of these minuses through you, and you didn't get, we got like people get square root of 7 instead of square root of 9 here. All over 2 times 2. But it should come out with plus 1 here, plus or minus 1 plus 8 is 9, square root of 9 all over 4. Well, square root of 9 is 3, right? 1 plus 3 over 4 is 1. 1 minus 3 over 4 is minus a half. So there's 2 solutions by the quadratic formula, or by factoring if you tried factoring, but I said use the quadratic formula. So this equation is equivalent to u or sine x, sine theta, equals 1 or minus a half. Well, equivalently, sine theta equals 1 or sine theta equals minus a half. Now it's trig function equal a number. I solved those on the unit circle, right? So quadratic equation and trig function say u equal the trig function and solve the quadratic equation, such as by the quadratic formula. That gives you trig function equal a number that you solve on the unit circle. So sine theta, the y coordinate equals 1, says I take this line here, y equals 1. Find only one point on the unit circle, hence only one terminal ray. And for angles at 0 to 2 pi, there's only one solution, pi over 2. On the other hand, if I solve sine theta equals minus a half, that's the y coordinate equal minus a half, halfway to the bottom of the circle at minus 1. I observe two terminal rays intersect the unit circle with that y coordinate. Now it's tempting to say, well, here's drop a perpendicular, this is a half, and this is 1. I recognize it's a 30, 60, 90 triangle. This must be pi over 6 right here. All right, pi over 6. And now you don't say, oops, pi over 6 going the other way. So you don't say the answer is minus pi over 6 because that's not in 0 to 2 pi. Instead, you go around this way and say, here's one angle, here's the other. So one angle, by the way, symmetry, this also has to be pi over 6, right? Also drops a half. So one angle is pi plus pi over 6 is 7 pi over 6. The other one, this angle, 2 pi less pi over 6 is 11 pi over 6. So there's three solutions, pi over 2, 7 pi over 6, and 11 pi over 6. That was it within one rotation. Didn't have to do anything fancy like find all angles and then drop the extras out because it was just sine theta, not sine of a multiple of theta. Didn't have to do more than one rotation. Okay. Let's get rid of that. So now we want to finish what we're doing with oblique triangles. We're learning how to solve these. We said we already know how to solve these by dropping a perpendicular, but this is going to give us a faster way to solve oblique triangles. Fortunately, it has to break up into two different cases. So we can drop the perpendicular. This is a symbol in mathematics for perpendicular, like two perpendicular lines. To solve these, remember an oblique triangle is any triangle that's not got a right angle in it, so it's non-right triangles. We can drop a perpendicular to solve these, but that's hard. That tends to give us multiple equations and multiple unknowns, but easier, faster for oblique triangles. We use one of two methods. I'll just review these because it's been a little bit. One is to use the law of sines. It applies to any triangle. It applies to right triangles too, but we don't use it for those because the right triangle trig is easier that we've already been doing, right? So you can do it with an extra step. We'll say the law of sines is easier for oblique triangles. And when it comes in handy to make it easier than dropping perpendiculars is if you're given angle, angle, side, angle, or side, side, angle information. If you're given three measures of those forms, you can always solve the triangle using the law of sines. It works every time. We went through the different cases last time. However, what happened in this last nasty case here, side-side angle? Yeah, in this case, there can be 0, 1, or 2 solutions. Because side-side angle is not a congruence theorem in geometry. You can have two triangles with the same side-side angle and different other measures. These two, however, are congruence theorems. If you know an angle followed by a side in a triangle, any other triangle with those same measures is congruent to it. It has the same measures, all six. 3 angles and 3 sides. But we can still solve them. It's just in this case, we might get 2 solutions or no solution. And the law of sines said this, and we did a bunch of cases. It says that for any triangle, we can label the sides. Suppose I put alpha, beta, gamma. It doesn't matter which side is labeled, which angle is labeled which on an oblique triangle. They like to put C for the hypotenuse in a right triangle, just convention. But for these, label it any way you like. Just put B opposite beta, A opposite alpha, and C opposite gamma. All right. When you do, the law of sine says this, that the sine of alpha is its opposite side A, as the sine of beta is to its opposite side B, as the sine of gamma is to its opposite side C. Which is really 3 laws, right? Because we could say this equals this, or this equals this, or this equals this. There's 3, but it's really the same law because, right, it's just, if you just relabel these things, move B over here and beta over here, and just rotate these things around, by relabeling, they're all actually the same law. So we'll say this is just one law up to relabeling the sides and angles, called the law of sines. And what happens is if you get a triangle with any of these given, you can use those 3 things to write one of the 3 equations here with 3 things known and 1 unknown, so you can solve for the last result. Maybe we should do an example for that one. This is kind of a neat example. I like the application here. This is one of your homework problems. Find the diameter of the circle. The diameter is the distance across going through the center point. Suppose I know this about the triangle. If I take a 110-degree central angle, right, meaning an angle from the center of the circle, this chord up here that goes between the 2 intersection points on the circle has length 8.3 feet or inches or something. What's the diameter of the circle from that? Kind of nice because it teaches you a little geometry too, right? But you got an idea how you solve that? Maybe I'll put this in your test next time. Huh? Again? This actually you can solve with a law of sine. You just got to think about it clearly. If this is a circle from within, this is the center point, then this is the radius r and this is the radius r, right? They're equal, making this an isosceles triangle. What do you know about the angles of an isosceles triangle? They're also equal, right? If you have 2 sides equal, the opposite angles are also equal. So this is alpha and alpha. And I observe that alpha plus 110 degrees adds up to 180 by the sum of angles theorem for a triangle, right? So I know that, which equivalently is 2 alpha plus 110 equals 180. And if I subtract 110 from each side, I've got 2 alpha equals 70 degrees. Alpha must measure 35 degrees. Hey, I know And now I see something that I could solve because I've got this triangle, 35 degrees, 10 degrees, 8.3, angle, angle, side. Or you could take this angle over here, 35 degrees, and call it angle, side, angle. Either way, you can use the law of sines to write an equation with only one unknown, so it's easier than dropping a stupid perpendicular usually. This time, it might actually be easier to drop the perpendicular, but we'll use the law of sines. So the law of sines says that the sine of 110 is to its opposite side, 8.3, as the sine of 35 is to its opposite side, which we recall as the radius, r and r here. Well, I just have to, I can use that to find r, right? Once again, we can cross multiply or take reciprocals. Let's take reciprocals and say 8.3 sine 110 is equal to r over sine 35. Multiply both sides by sine 35 and get r equals 8.3 sine 35 degrees all over sine 110 degrees. There it is. Now I've got the radius. Run out of my calculator. .3 sine 35, close. Make sure you close this parenthesis. It'll take the sine of the whole bottom also. Divided by sine 110 equals 5.066 roughly. Rounding off. I wanted the diameter. Remember, the diameter is twice the radius. It's just as clear across. So the diameter is 2r, is approximately to 1 decimal point, which is what the example asked. 10.1, right? Double this and it rounds to 10.1. There's a nice problem, right? When you can get angle, side, angle, or angle, angle, side, or side, side, angle, you can apply that law of sines. That works very well. Now comes the cases you don't want to use the law of sines. We mentioned last time, but we didn't say why. But you also have the law of cosines that also applies to any triangle. This is for side, angle, side, or side, side, side given. It's always true, regardless of whether this is what you're given. It's true for all those other cases, but if you use angle, side, angle, it will give you an equation with two unknowns. You're able to solve it right away. You have to write down two equations and two unknowns or something like that with two laws of cosine, something nasty like that. No good, right? So to get only one unknown in the equation, you apply it to a side, angle, side, or side, side, side triangle. That's it. And this gets to be really klutzy to remember. Angle, side, angle, which one was that? You know, if you just remember these two, use these for the law of cosine, side, angle, side, or side, side, side. Everything else is law of sines. How about that? Angle, angle, angle is only two independent piece of information, right? Once you know two, this one's 180 minus the other two. So we won't say we can solve a triangle like that. That just gives similar triangles. But all of the cases where you actually solve a triangle, there's 5 of them. And what you do is with 3 pieces of information, if this is the case, then use law of cosines. If not, use law of sines. How about that? And again, it applies to any triangle, but for right triangles, you want to use right triangle trigonometry. It's easier. If you have one of those cases, you prefer the law of sines because it gives you an equation with only one unknown. It's easier, right? So now what we do is, this is what it says. It says in any triangle, again, with the same listing as before, alpha, beta, gamma, A, B, C. C squared equals A squared plus B squared minus 2AB cosine gamma. And I gotta tell you, when I saw this thing, even years later, I hadn't used it a long time, I couldn't remember this thing. It's complicated enough. You really need some sort of, well, it's not like E equals MC squared. It's not just natural. It's a little longer. Anybody see a good way to memorize this one? This one actually does have a natural way to remember it. If I get rid of that, what have I got? Pythagorean theorem. It's a generalization of the Pythagorean theorem. I want to make this following note. When you have a right triangle, this still applies. You don't want to use it then because it takes longer than it's using right triangle trigonometry, but you can. When gamma equals 90 degrees, this becomes what? C squared equals A squared plus B squared minus 2AB cosine of 90. But cosine of 90 degrees is 0, right? 0 multiplying anything else is 0. It's the Pythagorean theorem. C squared equals A squared plus B squared. So what the law of cosines is a generalization of the Pythagorean theorem. It is the Pythagorean theorem when gamma equals 90, but now it does oblique triangles also, which tells you something very important in solving these oblique triangles. Don't ever use the Pythagorean theorem, right? It doesn't apply. This theorem proves that C squared is not equal to A squared plus B squared. You can't use the Pythagorean theorem. It's equal to A squared plus B squared minus 2AB cosine gamma. Unless gamma is 90 degrees, the Pythagorean theorem is wrong. So don't use the Pythagorean theorem on non-right triangles. So the law of cosines generalizes the Pythagorean theorem. To oblique triangles. How about that? There's another note. If you do the same thing you did with the law of sines, you can simply relabel the angles and sides. And then you come up with completely equivalent formulas here. If I rotate A, B, C, alpha, beta, gamma around, I also get the following result: A squared equals B squared plus C squared minus 2BC cosine alpha. Or if I rotate all the angles and sizes, keeping A opposite alpha, B opposite beta, C opposite gamma, I can get B squared equals A squared plus C squared minus 2AC cosine beta. So if I call this equation 2 the law of cosines, I can call this 2A and 2B. I like this one because it's the Pythagorean theorem minus 2AB cosine gamma. And I like it even better than this. In many books, maybe not most of them, but in many books, instead of using alpha, beta, gamma for the angles, they'll call this points A, the vertices of the triangle, A, B, and C. And so they'll say this is angle A, angle B, angle C are the angles at points A, B, C. And this will become, then it becomes minus 2AB cosine C, right? If you can use your ABCs, minus 2AB cosine C. That's Pythagorean theorem minus 2AB cosine C. That's how I can remember this anyway, because otherwise it's too hard. But ABC is easy, right? And that's better than this, where it's BCA or ACB, and I mean, okay. But that looks just like the Pythagorean theorem with the ABCs at the end. So I'll suggest that, but you'll see it written this way, either of these ways too, and you want to know where'd that come from. It's just relabeling the sides and angles from this one. It's just like the law of sines, you can write it 3 different ways by relabeling. Questions about that one? Okay, well, let's try an example then. I think this is a fun example. There's a lot of really neat applied examples in these sections if you look around, because everybody's doing some sort of triangles, you know, out in the open field, they're surveyor or whatever. You never get right angles. You frequently don't get right angles. And so you have to just measure whatever they are and solve the triangle. Well, we have this kind of case, 2 aircraft. This is one of your homework problems, actually. 2 aircraft simultaneously leave an airport, fly at the same altitude. The first travels due west at 300 miles per hour. And the second travels at 420 miles per hour, 25 degrees north of west. I think usually they put west of east or west of north or south, so it's kind of an odd way to put it, but we still know what we mean here, right? Here's the airport. One aircraft travels due west. If I make this north is up and west and east and south, just like standard map configuration, right? North, south, east. Here's that aircraft. And then the other one travels at 25 degrees, turn north. West at a faster speed, so it's out here somewhere. And the question then is, after 90 minutes, how far apart are they? There we go. I'll see if I can wake you up here. This one is reminiscent of my favorite one of my favorite math cartoons. There we go. This is the label has gone on the bottom. It's the mathophobic's nightmare. Let me see. Cartoon I got to put on here. Mathphobic's nightmare, right? Get up to heaven and okay, now listen up. Nobody gets in here without answering the following question. A train leaves Philadelphia at 1 p.m. It's traveling 65 miles per hour. Another train leaves Denver at 4 o'clock. So you need some paper and you got to answer one of these kind of problems we're doing here. This is the mathphobic's nightmare. I thought it was a pretty good cartoon. Anyway. coming back to our problem at hand, just in case you get this one asked on your way to heaven. How do you answer this one? Well, the question is, what's this length here? C. Let's label. I like D for distance usually, but since I'm doing the ABC law of cosine, I'll call the side C, right? And so the object is to find C. What are these other two sides? Like, I know I can figure this out. If it's going 300 miles per hour due west, how far is that? We call the side A. Yeah, if I'm going 300 miles per hour. Instead of writing mph, I'm going to write miles per hour this way, miles divided by hours. And then I multiply it by, instead of 90 minutes, I'm going to write that as 1.5 hours so that units will cancel. Units of hours cancel with units of hours. So this one goes 450 miles. There we go. Over on this side, plane travels 420 miles per hour like that, or 1.5 hours. Written that way, the hours cancel and I get 630 miles on this side. And now I recognize in this triangle, I've got side followed by angle followed by side, or you can go this one, side, angle, side. Just so they're all in a row. It's side, angle, side. So I'd use law of sines or law of cosines. Cosine, yeah, side, angle, side, and side, side, side. The law of cosines will give me all but one letter known when I put it in right. Now the trick on this one is you have to use the angle that's in here, and that angle is opposite C, it's gamma. So I need to use the law of cosines that has gamma in it to give an angle. And I'll say, here it is, it's my favorite, C squared equals A squared plus B squared, the Pythagorean theorem, minus 2AB cosine C, right? BC's. Except I'll write gamma to follow the book instead of C. Gamma is actually not the third letter in the Greek alphabet either, but we always use it with C for some reason. I don't ask a math historian, I suppose. All right, so C squared is that. And now A was 450. B was 630. So I got 450 squared plus 630 squared minus 2 times 450 times 630 times cosine of gamma is 25 degrees. There's what C squared is going to be. And if you get a negative number, you made a mistake. Because this applies to any triangle, right? So let's see, 450 squared plus 630 squared. Let's see, 900 times 630. Cosine 25 degrees. It is the law of cosines. I get 85, 523 point some other stuff. We'll just say approximately that many miles to the nearest square miles squared. It's C squared, so it's miles squared actually. Now what's C? It's just the square root of that number then, right? C is square root 85, 523. It's about, let's see. $292 miles. So the planes are about that far apart after 90 minutes. But you see, this has all sorts of nice applications, right? And they use this in triangulation and finding locations on the Earth if you know, positions and angles. You got the radio signal coming from here, we said, and two observers who know how far apart they are, and the two angles, you use the law of sines. If you knew two sides and an angle between them, you like in this problem, you can use the law of cosines. Okay, feel comfortable with that one? Just know. So, here's a surveyor's problem. My wife's dad is a surveyor. So we went into this kind of thing. Uh, Suppose a garden, if you go out and measure it, is triangular with side lengths A equals 30 feet. Maybe you just cut 3 boards of these length and made a garden out of it, right? And make something artistic. B equals 40 feet. And C equals 60 feet. This is kind of like when you're doing right triangles, a 3, 4, 5 right triangle. This is clearly not a right triangle, right? It'd be 30, 40, 50. 34, 60 is an oblique triangle. I can sketch it. That's kind of a nice thing to do. Here's 60. Here's 30. And here's 40. Solve the triangle. In other words, 5 to 3 angles. Maybe I want to cut these boards so they meet at the right angle and I can screw them together nicely without having corners jutted against each other, right? What angles do I have to cut these boards at if they're 30, 40, and 60 feet? Well, it's side, 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 right? So I use law of cosines, right? Side angle, side, and side, side angles, and side, side, side are law of cosines. All the rest are law of sines. So which one do I use? There's 3 of them, right? Turns out it doesn't matter, right? I've got all 3 sides. I can find any angle I want, except it kind of does. What you preferably do is take the angle that's opposite the longest side. Well, I'll call this gamma, and then this is C, and this could be B, and this could be A, making this alpha and this beta. Start with the larger angle. How do you know which one is the largest angle? Yeah, and any triangle is opposite the largest side. And I'll show you why that's useful later. It saves you some trouble later. So it's all, you can use any one of the 3 laws, they all apply and they'll all work at the first step. But if you do the one opposite the largest side, that saves you a little trouble. And so what I'll do is the largest, if I want to solve for the largest angle gamma, then I need to use the law of cosines 2 that has gamma in it. All right, c squared equals a squared plus b squared minus 2ab cosine c, or gamma. And now let's see, 60 squared equals 30 squared plus 40 squared minus twice 30, 40 cosine gamma. And sure enough, the law of cosines, I know every number but gamma. So I can solve this for gamma. Right? This takes a little algebra, right? Well, let's see. I subtract 30 squared and 40 squared, and I get 60 squared minus 30 squared minus 40 squared equals this number. What number is that? Well, that's 1,200 times 2. This is 2,400. So equals minus 2,400 cosine gamma. Well, that's a little simpler. Now this one, if you work it out, comes out to be 1,100. So if I divide, I find that cosine gamma is minus 1,100 over 2,400. 1,100 over 2,400. easier than that. Who wants all those zeros on there, right? Just divide top and bottom by 100 and get rid of those, call it minus 11/24. Evidently, gamma might be the arc cosine of negative 11/24. Wait a minute, maybe it's like the law of sines, where there's a ambiguity. Maybe, remember the law of sines, when you had sine of an angle equals a number, it could be the arc sine or 180 minus the arc sine. Either one could happen in a triangle. So we had that difficulty all the time. Not so with the law of cosines. There's no ambiguity here. No uncertainty. It's always the inverse cosine. Why is that? Anybody kind of see it? If you got a little, put your thinking cap on for a second, you can probably figure it out. Why would it always be the arc cosine? Gamma is a solution to cosine gamma equals a number in a triangle, or gamma is an angle in a triangle. It always has a solution. This is always one solution, right? To cosine gamma equals a ratio in a triangle. So it's always a solution, and it's the unique answer it's the unique answer between 0 and 180 degrees, right? Cosine gamma gives you the unique angle between 0 and 180 degrees, whose cosine is this number, but the angle in the triangle is the angle between 0 and 180 degrees, so that's always it. This always gives you the angle that you want, and you don't have to worry about a second case like you do with the law of sines. Let's just compute that and see what it is. Degrees mode again, inverse cosine. Negative 11 divided by 24 is 117 degrees. Wait a minute. Cosine of a negative? How can the cosine be negative? That actually happens in a lot of the problems, right? This just means it's in quadrant 2, right? So whenever you're going to get an obtuse angle, you'll always get a negative cosine. So this is okay to get cosine equal to negative. This means you're going to get an obtuse angle. The angle won't be negative. It's 117 degrees. So there's one of my 3 angles I needed. I'll call that step 1, right? Solve this triangle. Start with the largest angle. Now I've got 2 more angles to find. So how can I find another angle? Now I've got 2 tools in my tool shed, right? I can use the law of sines or the law of cosines. It doesn't matter. They both work. However, if you looked at this game here, it's kind of, law of cosines is a little more complicated. So the law of sines is actually easier. It's a little shorter. Almost every book I ever remember used the law of sines as the second step rather than the law of cosines. You can use the law of cosines, it works just fine, right? I don't care on the test, whichever way you like to do it. I'll use the law of sines because it's shorter. Well, how do I use the law of sines? I now have this angle, so I can say sine of gamma, 117, is to its opposite side, 60, as I can find either angle I want, it doesn't matter. Sine, let's say beta, is to its opposite side, b equals 40. There's the law of sines, if I choose to do it that way. Multiply by 40, and I've got sine beta equals 40 sine 117 over 60. Evidently, one solution is beta equals the arc sine 40 sine 117 over 60. Wait a minute. What if it's 180 minus? Remember when you got this law of sines? It might be 180 minus. How do I know it's not 180 minus? This is a real subtlety that threw me when I was first trying to teach trig. This is why you start with the largest angle. In any triangle, there is at most one obtuse angle, right? If this is greater than 90 degrees, obtuse, it means bigger than 90 degrees. Then, since the 3 triangles add up to 180, each of the rest of them are less than 90 degrees, right? So you can have at most one obtuse angle in a triangle. So if I find the largest angle first, I know the other 2 are acute, right? So I found the largest angle. This must be acute because gamma was the largest angle. Started with the largest. So there isn't any ambiguity. If I take 180 minus that, I'll get an obtuse angle. That's wrong. It must be the arcsine. There's only one choice left. So when you're doing the law of sines at the first step all by itself, the answer might be arcsine. It might be 180 minus arcsine. But when you've already found the largest angle, then it's only the arcsine. It's not the other one, right? Not 180 minus the arcsine. So let's compute this, and that'll be the answer. Inverse sine. I don't have to do two cases. 40 times sine 117 and close it, right? Divided by 60. About 36 degrees to the nearest degree, 36.44 actually. So the second angle is 36 degrees. I think that's on screen, yeah. And so now how about, I've got one more angle to solve for the last one. What should I use for the last step here? Just to put you to sleep, I need another cartoon. I could use the same thing. Well, what's even easier? There you go. Yeah, 180 minus, right? Last angle by the sum of angles theorem. So you just take angle alpha is 180 less the 117 for C, less the 36 for B, gives us 27, right? 27 degrees. Yeah. Now I've got all three angles. So to make it easy on yourself, this saves mistakes when you don't have so many calculations too. Law of cosines, law of sines, sum of angles theorem is the quickest way to do the side case. Now, congratulations, you're all experts in trigonometry. That's the last pure trigonometry we're going to do. Everything else the rest of the semester is going to be applications, which are also an important part of almost every trigonometry course, but they aren't trigonometry really. They're applications of it that are so common you need to know them when you take the course. So there it is. We can solve right triangles using the right triangle trigonometry, right? Sine equals opposite over hypotenuse kind of laws. We can solve oblique triangles with these. We have identities to simplify and to prove new identities. And we have abilities to solve trig equations, right? So all those things come together. And now we can do some interesting problems. So here is the first application of the course. Is area of a triangle. You can use trigonometry actually to find area too, not just to find the angles and sides. In the special case that you're given side angle side data. We're going to do two methods for area of a triangle. And this first one I want to prove, because if you forget the formula, so maybe you'll remember the proof and be able to figure it out. So the first method is given side angle side data, like in the law of cosines. The area of a triangle is, well, let's suppose it's done like this. Here's my triangle. And suppose I call this side A and this side B for base and this side C. Again, it doesn't matter which one's longest in oblique triangles. But how do I find the area by geometry? Remember the geometry formula for area of a triangle? What is it? How do I find the area of a triangle? How do you know this? From geometry, what's the usual formula?
Times height over 2.
Yeah, 1/2 base times height, exactly, right? Okay, I'll put B for base, I'm in good shape, but I need the height. So I'll drop a perpendicular here. Right, Euclidean geometry says I can drop a perpendicular to any line from any point. And now What is H? Well, by trigonometry, this is where trigonometry comes in. The sine of this angle, let's see, it's opposite C, so it's gamma. The sine of gamma is H over A using right triangle trigonometry, right? And if I multiply both sides by A, that tells me that H is equal to A sine gamma. And I can put that into here. 1/2 base times height is A sine gamma. And then I rearrange the order of the letters and I write this 1/2 AB sine gamma. And once again, that other notation where you call the angle opposite side C a capital C, then it becomes ABCs again, 1/2 AB sine C this time. So I like it that way, ABC in order again is the way to memorize this nice formula. I'll put 1/2 AB sine gamma just to follow the book's notation, and most people use Greek letters, I think, these days. There it is. So this is a theorem that we just proved. The area of any triangle with labeled this way, the usual way, is A equals 1/2 AB sine C, or gamma. There it is. There's equation 5 or something. How about that? Trigonometry solves the area problem. And you just have to remember, gamma C is the side between sides A and B. This letter not being one of these two, it makes it the angle between these two. So it's a side angle side case only. Here's an example. Suppose I had done my garden this way. Suppose I made the side 30 feet here and 60 feet here. I measured the 36 degree angle in between. And this is the creek flowing behind my house back here. And maybe I didn't even know this is 40 feet on the other side. This is the triangle we saw before, 30, 40, 60. Suppose I've got this triangle and I'm just trying to figure the area of my garden that's bounded on one side by the creek. And I want to know how much mulch do I need to put in there, so I need to know how many square feet that is. How do I find how many square feet given those measures that I just measured 30 by 60 and 36 degrees by protractor or something? Oh, it's right there. I just call this A, B, gamma. Now this is different labeling than we had before. Before this was B, this was beta, and this was C. So I've used different labeling, but nonetheless, for the area, I just say, oh, it's 1/2 AB sine gamma, since gamma is the angle between sides A and B, side angle side. This is 1/2 times 30 times 60 times sine 36 degrees, and that triangular garden I had before now has this area. Looks like 900 times sine 36 degrees, right? It's 529, what? Yeah, square feet, since it's an area, right? So you can take 529 little 1 by 1 squares and fit them in there, breaking them in as you had to fit along the edges. There we go. It's a nice formula for finding area using trigonometry, the sine function. I'm just about out of time. Maybe I can do this last one. I like to get this one done because it goes naturally with the one we just did. This one actually has no trigonometry. It's so ancient, it goes back to an ancient Greek. I don't know when it was around, somewhere around 2,000 years ago. You can look it up on Wikipedia or something. The last formula is Heron's formula. an ancient Greek he was, for triangle area given side measures. So if you know all three sides, like if I just know those three boards like we had in the first case, here's 30 by 60 by 40 maybe. What's the area enclosed in that thing if I cut those three odd lengths? Oh, well, here's the formula to the Heron. The area is computed like this. Let D be the sum of the three side lengths divided by 2. Then the area is always the square root of D times D minus A times D minus B times D minus C, just like that. This one we won't prove. We're out of time, and it's not trigonometry, and it's not trivial. It's not worth it. But nonetheless, it's a nice formula going back to antiquity that computes this. And so on this one, I compute here. Do it quickly because we're out of time, I think. The area is, we compute D first, is the sum of these over 2, not the average. 30 plus 40 plus 60, all over 2 is 65. From that, we compute the area is the square root of 65 times 65 minus 30 is, let's write it that way, times 65 minus 40 times 65 minus 60. There it is. And these parentheses on your calculator are terrible. You always make a mistake, so subtract in your head. Say it's square root of 65 times 35 times 25 times 5. Do that part in your head. And now you've got, let's see, square root 35 times 25. Square root 65 times 35 times 25 times 5. 533 feet. Why did I get a different answer? 533 square feet? Why didn't I get 529 again? This is an important thing when you're doing these numbers for applications, not so much in the class. These are actually both right. When I rounded this off to 2 digits, it means all my ensuing answers are only good to 2 digits. The third digit could be anything. So you only say this is good to about the nearest 10 feet. It could be off by 10 or 20 feet. So the fact that these are close to within 10 or 20 feet means these are probably both right. But this one, I rounded to 36. I threw it off. I should have gotten closer to 533. This one's more accurate. All right, try section 8.2. All the problems on there in 8.1. This is the law of sines. This is the law of cosines. See if you have questions next time. And this will include some area problems actually too.